Hey folks, you're a very good developer. Probably. Regardless, you do write bugs. That's unavoidable. What is avoidable is wasting time trying to track down the cause of those bugs. Sentry.io provides full stack error tracking that lets you monitor and fix problems in real time. You can see the severity and the scope of the error, get immediate access to the stack trace, connect the problem to the commit that caused it, and fix it without delay. Sentry, it's a name so common that they have to include the top-level domain in their advertising to make sure you remember it. Sentry.io. That's Sentry.io. Open source, full stack, web apps, native apps, mobile games, smart oven mitts. If you can program it, they can make it far easier to fix any errors you encounter with it. Your code may be broken. Let's fix it together. Visit Sentry.io. Hi, this is Scott Hansel, and this is another episode of Hansel Minutes. And today I'm talking with Tuur Stuyck. He is a postdoctoral research scientist at Facebook Reality Labs. He's worked at Pixar, and he's written a great new book called Cloth Simulation for Computer Graphics. How are you?
Hi, I'm good. How are you?
I'm very well. I'm happy to be talking to you. I'm trying to learn as much as I can about games and computer graphics and how things are built. And I had a gentleman on a couple of weeks ago talking about the game engine behind Doom. And now you've got this new book out, Cloth Simulation for Computer Graphics, a little light reading. And I'm excited to talk to you about it. This is not necessarily a 500-page book about like science. It's really quite accessible, isn't it?
Yeah, I think that was the main goal that I had is that if you want to try and get into like any type of simulation, it's usually very, very dense math and very technical terms. And I tried to write the book, which is more accessible with a little bit of background story, how like people use it in industry, where all the algorithms coming from, what does the math actually mean more intuitively.
So this is like not intending to be an overview of all things happening in the space, but rather an on-ramp into the space.
Exactly. So it's not covering like the latest years of research, but it gives you a very nice introduction or like the different steps you would take if you were to get into this type of study. So it starts with very simple simulation techniques, which of course have some like many limitations, and then it steadily advances to more complex techniques. And we do actually mention a technique that is used in industry today, but of course there's many other additional techniques that have been developed since. So it's definitely not covering the latest and greatest research, but if you understand everything in the book, it should be straightforward to go to those research papers that you can find at like SIGGRAPH or other conferences.
Now, when I hear about what I think as a layperson are highly specialized or highly technical things, I think to myself, oh, there's probably 3 people in the world that care about this. But in fact, you say that this is actually a vast amount of people doing research in this space. And every year they're creating new literature on cloth simulation.
I wouldn't say vast, but there's definitely a fair amount of people working on it, just because there's a lot of applications at the moment, I would say. So it's heavily used in movie production for special effects or animated features. And then also there's the fashion industry, which use maybe virtual prototyping or virtual fitting rooms. So it definitely has a lot of applications, which makes it interesting for people that work in the field.
Mm-hmm. And do we only care about cloth simulation for, making the guy in Assassin's Creed like run more realistically, or what are other use cases?
Well, that's a great use case, of course. But other use cases are, like I said, movies. So any movie that you go watch, if it has special effects like explosions and whatnot, or virtual environments, it probably has some sort of cloth simulator in it too, maybe for simulating leaves or actual clothing on characters. And obviously for animated movies, all the clothing, maybe the curtain or a flag waving in the background, those are all simulated materials. So that's one more of the entertainment industry applications. And I think one other big application is like I said, like fashion. For instance, like online retail, I think a lot of companies would love very fast computer software that can simulate clothing on virtual bodies so that people can try on clothes virtually before buying them, because that would have a lot of economical impact, of course.
Wow, that's interesting. That would imply that I could potentially, I'm just imagining some future world here where I put on my VR headset and at some point I've either scanned myself with a webcam or with my phone, and then I stand in a virtual place and try clothes on, basically.
Yeah, exactly. And then the idea is that you have your own body model that's a good estimate of your own body, and then you can try on the clothing, and then they should represent the actual physical clothing, and then you can see if it drapes well on your body, if you should go like get a size bigger, get a size smaller. It's like going to a store and actually trying it on, right? So you can actually see it draped.
Yeah, and it doesn't feel like we're that far away from it. I noticed recently when my iPhone updated, it has a measurement tool that allows me to basically use it as a virtual ruler just by moving it in space. It's pretty straightforward to extrapolate to a world in the next couple of years where I could do this.
Yeah, I think it's definitely possible. There's a few more engineering things to overcome, of course, and make it fast and reliable, like any good
Mm-hmm.
application. But it's definitely not far fetched to have it in the next coming years. It's probably not 10 years out.
Mm-hmm. I've read some of the papers that you've published, and I've looked at different articles as well as some animations that have come out with various papers in the space. And it's one of those things where I think when it works, we as the lay people don't think about it, but when it doesn't work, we go, "Wow, that virtual person is really awkward looking."
Yeah, that's the difficult thing, and especially with people and their faces, it's really hard to convince people. But usually for clothing, unless you work in clothing like in the simulation of it, like me, you don't typically focus on what people are wearing. Like, are the folds realistic? Does it collide with the body, or does it have like accurate friction models? I think as a viewer, you're typically focused on the face, which makes it really hard to recreate the face. But we get away with like the clothing a little bit easier.
Mm-hmm. I have a friend of mine who has a master's degree in costume design and another degree in something around like English history or English literature. And they went to see like Robin Hood or something. And she said that she had to walk out because as a person who is an expert in the space, she was like, I couldn't focus because the stitching was wrong on Robin Hood's, shirt. Like that stitch wasn't invented until whatever. I wonder if in your space, now that you're doing postdoctoral research, do you have trouble going to see a movie and you just go, I can't watch this because that cloth is completely wrong. That flag is totally distracting me.
No, nothing. Not that it's wrong, but I definitely do have to watch it twice. Once to focus on like the clothing and the simulations, like how did they do that? Where did they like did some manual tweaking? And then once for the story, of course. So it's not like I can't watch because it's not good. Definitely not. But it's more like out of interest. Like how did they pull this effect off? How did they do that?
That's good. So for the most part, you're not watching to hate, you're watching to appreciate.
And to learn, right? So yeah, for sure.
And I read in an article that Pixar had a challenge with the movie Coco because the bodies underneath the cloth were not really bodies; they were skeletons.
The problem that they had is that skeletons are really pointy, and it was hard to make it collide with the clothing without it puncturing through the clothing. So yeah, David did a whole revamp of the simulation engine to fix all of that.
Mm-hmm. So is that an engine? Like speaking about how you would do this for a movie, I'm imagining that you get it mostly right, and then the director of the movie says, well, everything's great except in this one part where he turns his body, this is wrong. Do you have to then go back and rebuild your engine and change your equations?
It's not necessarily like that low level that you have to change your equations. Typically, or one would try to find constraints or extra additional elements on top of it. You build on top of it to enforce certain like director comments or anything like that. Yeah.
How does that work? Maybe you could explain the pipeline a little bit, because from the outside, I know that there's the 3D modelers, but there's also the people who make the tools that make the movies.
Mm-hmm. Yeah. So there's a lot of people involved, of course, but the big picture is that you have the artists and they create the clothing garments, and the garments are then used as the initial state for the simulator, and then the simulator will take body motion and the environment, such as wind, gravity, and then it will advance the simulation forward in time, so you get the moving clothes on the body, and then you get your simulation result, which is a video of the clothing, and then typically you would show it to the director, and they would say like, oh, I like it, or I'd like to request some changes. And then the artist would go back and try to change the simulation parameters, maybe like change gravity or the wind, or maybe have like explicit constraints that you put onto the clothing to make it do certain things. And then you kind of iterate over that so you can finally get the result that you want.
Do you think about the state of the cloth in the sense of, I mean, I suppose you could model it like the universe, like the quantum machine that we live in models it, and think about the molecules, or you could think about it in a more holistic view.
Yeah, I think in graphics, since we're not necessarily concerned with the right solution, but more with a reliable solution that looks good, we tend to discretize just using triangles, because that's very typical in computer graphics, and computers are optimized for that. So
Hmm.
like the clothing would be divided into little triangles, and then we would simulate over that.
Okay, so then you're thinking about it as a continuous, like elastic sheet.
So there's you have to read the book to get the full the different methods, but there's different approaches to it. So one, I would say the most simple approach is probably just like do look at it as like a bunch of point masses that are connected by springs, and
Hmm.
then by doing that, you can create something that looks like clothing, but it's of course not very physically accurate, right? And then more advanced models is where you actually look at the triangles as little sheets of cloth, and then you simulate over the triangles, so they're not just separate masses that are connected.
So over the decades of research in this space, over the last 40, 50 years, when people have been thinking about these things, when computers are starting to get to that point, are these varying ways to express cloth something that comes out, we use it for a while, and then we get rid of it and we stop doing it and we now use the new way? Or is it something where there's a toolbox of several ways and you can really use them on a case by case basis?
There's definitely a toolbox, and I guess it depends on your use case. Like if you like, you probably wouldn't use the same algorithm for a game as you would for a movie, just because the quality's so different. But then again,
Hmm.
like one is really fast and one is slower, so you kind of have that trade off there. Um, I think the algorithms are pretty stable, but you get these additional research findings, where it's like maybe a better collision model or maybe a better friction model, and you can
Hmm.
swap out components or add in to like your existing solver. But I don't think it's very typical that people would like write a new solver every year or every other year just because a new technique came out.
I
Um,
see. So, looking in the overview of the book, as you kind of walk through the research from the 80s through the 90s to the late 90s, as people start to learn what is either the right way or a way that is going to work, moving up into triangle-based cloth simulations in the late 90s, when did people start thinking about the state of the cloth? Like burlap is going to move differently than silk, and if it's wet, it's going to move differently than if it's dry.
Yeah, so that's kind of like this is the graphics approach to things, and then there's also the engineering approach, right? So there's
Mm.
the textile industry they use different models which are much more accurate and take the material parameters into account. Whereas
Hmm.
graphics is we have different material parameters, but we're mostly interested in how does it look and how does it behave, rather than if I apply this much force on it, how much millimeters would it like stretch or something like that, right? Which is a very engineering kind of purpose that you want. So people
Oh.
have definitely been interested in, because you want to simulate different materials and you want to have it behave like different materials. But usually, I would say that there's some sort of library of coefficients that have been developed by an artist or someone that says like, oh, this is linen, this is wool, this is leather. Um, but it's not necessarily you don't necessarily have to like do the actual stress tests on a mechanical bench and get those coefficients from there, because all
Hmm.
the simulation methods are approximate too, right? So
Well, ultimately, they're just picking a number that looks right.
yeah.
Like, for example, I had someone on recently who worked on flight simulators,
Hmm.
and she would go up in the actual airplane with like physical mechanics, physical equipment, and measure G forces as she spun around in the thing, and then come down and then make sure that her software, expressed reality,
Hmm.
which was more interesting to her than what it looked like. It had to feel right.
Yeah, yeah.
Yeah.
Um, yeah, I think for graphics, we're mostly interested in what it looks like. But then, of course, if you want to validate your software, it has to have reasonable results, right? So you can definitely compare it to reality, but it's not that um, it's like the ultimate test is to get exactly what reality does, because there's so
Hmm.
many. You have discretization error, like approximations, and like if your triangles are big, it's not the same as having really small triangles. There's like friction models. You're colliding with the world, so you have to like model the world perfectly too. So it's really hard to recreate that physical world in a simulation, I would say.
Hmm. And what kind of improvements have happened in? Is it just algorithmic improvements, or is it also the fact that the people making the algorithm know that processors are 100 or 1,000 or 10,000 or a million times faster than they were when the original algorithms were created?
Yeah, so there's definitely the hardware is definitely important recently, and especially with GPUs becoming really important. Different types of solvers have also been developed. So one thing that comes to mind is position based dynamics, which parallelizes really really well. So that would fit really nicely onto GPUs. So yeah, there's definitely a relation between algorithms and hardware that is used these days.
And when thinking about 3D graphics or a game where you have to do it in real time, I wonder, do you have to simulate, like, for example, someone's running and they're wearing a dress? Do you simulate the totality of the dress, both what can be seen and what isn't seen? Because what is occluded or what is behind the person might affect how the cloth drapes in the front, or can you optimize by only draping what can be seen?
Well, that's hard, of course, because what if the character turns around, right? Like the cloth needs to have a state like for the whole garment, right? I think for
Mm.
games, what typically would be done is you have two resolutions of the garment, and one is the simulation mesh, which is the geometry, which is usually pretty low resolution, and then one is the what we call the render geometry, is which we show to the user, which is what is actually seen on the screen. And so this is more higher resolution. And then we deform the high resolution with the results of our low resolution simulation. So we get these details on the garment, maybe like a bow tie or buttons
Mm-hmm.
or like stitches from the seams, but we don't actually simulate all that detail. But by deforming the high resolution with the movement of the low resolution, we can kind of fake simulating the whole thing.
Ah, interesting. And then I suppose that could be that resolution of the mesh, the resolution of the how the cloth drapes versus the texture of the cloth could be on a person by person basis. Like someone with a big thick dress would need lower resolution than someone who has on only a t-shirt. Like what I'm saying is that you would need higher resolution and more triangles if the detail mattered of a close up, or the closer the person got to you, or the thinness of the fabric. And you might say, yeah, well, the wrinkles don't look right because the underlying mesh is too coarse.
Yeah, exactly. And it's also collisions with the body, right? Like if your triangle hits the body, you don't want to go inside the body, but if the triangle is really large, it might create artifacts because you're pushing the whole triangle out. Whereas if it's smaller, it would be more of a subtle effect. So yeah, there's definitely the trade-off between like high resolution is better quality, but it's also slower, of course.
Oh, interesting. Okay, so then that means that the triangle size or the size, the granularity of the mesh, and forgive me if I'm using the wrong terms here, would change based on where it is on the body. If it's in the armpits or on the elbow, you'd want more detail than if it were just draping around the legs.
That's yeah, something that definitely could be considered as an optimization. Yeah.
Ah, interesting. This episode is sponsored by Stack Overflow for Teams, a private, secure home for your team's questions and answers. It's everything that you love about Stack Overflow, now for your company. Get instant, reliable answers from your coworkers without disrupting them. Unlike documentation or wikis, long email threads, or distracting instant messages, Q&A mimics the way that we naturally share and find information. Introduce Stack Overflow for Teams to your company and start building products faster and better. Visit s.tk/Hanselminutes to get your first month free. That's s.tk/Hanselminutes. At what point, if you're making a movie, though, does your algorithm get into the face of the art director, where it's correct and it looks okay to you, but they want on a frame by frame or scene by scene way to change things?
Mm-hmm. Yeah, this is actually very common. The simulator will tell you we're approximating physics, so the simulator would tell you like, look, this is what physics would do, right? This is what the real world would like. It's approximation of that. But then for movies, and especially like animated movies, which can be highly art directed, the clothing of the characters kind of gives something away about the character. Maybe the villain in the movie would have like more like pointy clothing, or the silhouettes would be more like sharp edges, whereas like if it's someone you're supposed to like in the movie, the clothing will be softer, where the folds will be like rounder and not as like crisp. So these are these very subtle cues that the director wants to give to you as a viewer, to ask to like, is this going to be a good person in the movie or a bad person in the movie? So artists definitely want this control over their simulations, where they can specify where they want folds to form, how big should these folds be, when should they form. So there's definitely a lot of research and know-how that exists in these big studios to create these simulations, to adapt them, to do exactly what the artist wants. And I think this is typically called art directability. So this is something that you run on top of your simulation algorithm to enforce what the artist wants. So you kind of you make it art directed. So you follow what the artist says it wants you to do, but then you also use physics to have something that looks believable to the viewer. So you have to try to find this trade-off between realism and these goal states that you're trying to hit.
It seems like whether it's movies or games, that there's definitely this push towards photorealism. Everyone wants it to look hyper-realistic. I wonder, though, is that the same movement within cloth? Are you always wanting it to be as realistic as possible, or do they ever just say, well, forget physics, I want it to look like this?
Well, it's there's different things that you're interested in, right? So one thing is you want it to look really realistic, and you want it to be effortless. Like you just want to press
Mm.
start, and you want it to do what you want. But for simulations, this is typically not the case because there's a number of things you have to take into account. Like the simulation can fail sometimes. Like if you miss a collision, then you have like a poke through, like the body coming, or like the clothing is penetrating the body, which is not. It creates visual artifacts that you don't want, right? It's like the wrong solution to the problem. And then other things that you typically have with these numerical algorithms is that they're not always stable, which basically means that if your time step to advance the simulation forward in time is too big, you can have maybe oscillations or the simulations producing really weird behavior or visually disturbing behavior. So there's things like that that you have to take into account. So I think realism is definitely a big important thing, but then also the stability or the reliability of the algorithm is important too. Because
Hmm.
if you run a simulation that's going to take maybe for a movie it might take like several hours, you kind of want like to reliably know that it's worth running those 2 hours and not like seeing that oh it failed after like 2 frames, right?
How different are the tools and implementations that focus on real time as the goal versus the ones that are offline, more like creating a movie? I assume that they don't necessarily render a movie from Pixar in real time.
No, definitely not. Yeah, I think the one of the things that it's notable in the algorithms is that the more the slower the algorithm, the more accurate usually. So they will like model the real world better. Whereas for games, you're interested in the dynamics and you want something that looks good and is very reactive to the player movement. So you use something that's maybe more approximate but really fast.
Are these things being driven by data? Like, can you pre-process how clothing moves? Can you look at it, analyze cloth behavior in real time, and like store it in some kind of a machine learning model and teach machine how things move? Or is it always more like ray tracing?
No, there are definitely like data driven approaches that exist. Uh, in research, there's been a lot of papers that have been published on this, where you would maybe do a low resolution simulation, and then you would like try to place wrinkles on top of the clothing based on simulations you've run in an offline process before that. So you know, like, oh, if I make this movement, these wrinkles will form. So you can kind of copy over that data onto the geometry. And then more recently, there have been more like machine learning AI techniques where they they learn a model that can add details in a UV space in a normal map. So you can have these really fast like you have a low resolution simulation and you can add details um, based on some machine learning approach.
Okay, interesting. So I'm trying to visualize the layers here. There's the potentially the mesh layer that is the cloth in a low resolution group of triangles, and then
Yeah.
there's the texture over the top of it, and then the normal map goes over the top of that.
Yeah, so the normal map is how it there's this paper called Deep Wrinkles, and what they do is they use a normal map to change the normals locally on the surface, so they can add wrinkle detail in the texture, like in the viewport, based on how
So
the light gets how they affect the surface.
it's so interesting to be like a an armchair quarterback because you know how you watch football and you go, I can do that.
Hmm.
Like when I read the Deep Wrinkles paper beforehand, I was like, of course, that's how you do it. Like after the fact, like I get it now. How often does that come up in the space of research where someone comes up with an idea and then everyone's like, oh yes, it's been out there just waiting for someone to pluck it out of obscurity. This idea.
The idea is definitely good, but it's not. It's of course a lot of work to first get the idea and then prove that it works and then validate the model compared to other methods. So I mean, there's definitely times that you think like, oh, that's a great idea. Wish I had a thought of it. But even if you did, it would still have been a lot of work to actually implement it and prove that it works, right? So
That's a good point because in the
yeah,
space of academia, you can't just have the idea and write a blog post. You have to have the idea and then write a 20-page peer-reviewed paper where 19 of the pages
yeah,
are
comparisons and
appendix.
validation, and there's a lot of work to publish a paper. Yeah, for sure.
Does this feel like the space that you've chosen to live in, the space of cloth simulation? Does it feel like something that it'll ever be done and it'll all be commoditized, or will there always be room to improve?
I think there will always be room to improve, especially with like new applications in virtual reality or augmented reality opening up, where we want like lower energy consumption. We have the hardware is not as good as computers, but we want everything in real time visualized. You have to share the processors with different different algorithms and stuff like that. So there's definitely a lot of stuff that has to be done before we're there. So it's going to take a while before we get that.
There was an amazing thing that I saw in a SIGGRAPH 2008 paper. This is 10 years ago now.
Hmm.
That was simulating knitted cloth at the yarn
Yeah,
level,
yeah,
which gets me thinking about like texture. Like a sweater is a very, very different thing than like a fleece.
yeah. That's really cool work, and that's from Stanford, I think, and they're working on it, working on more recent work on that too. So that's very interesting to see how they can do like actual yarns and how the individual yarns are colliding, or if you pull one, how it affects like the whole structure. Yeah, it's definitely very cool work.
Which I think it would be even interesting if you were doing a movie and then in the movie a piece of the yarn gets pulled on, and then how does it affect the entire outfit? Like the yarn in their simulations, at least in 2008, was perfect. But
Hmm.
when it's not perfect, then things really get interesting.
Yeah, yeah. No, it's definitely interesting. It also has applications in more like the traditional industries, such as
Mm-hmm.
like the companies making knitted clothing. Maybe they can do virtual prototypes and get better understanding of what it will look like, or they can optimize over like material use, or how are they going to do their stitches. So they can do the way I understand is there's different type of stitches you can do. So maybe they can like see like, oh, I'm going to try this pattern, and they can get a really accurate visualization of what it's going to look like and how it's going to drape and move. So that
Mm-hmm.
would definitely speed up their design process too.
If someone is listening to this podcast and they're thinking about either the game or the thing that they're working on or the movie that they're working on in their spare time, where do they get started? Do they have to get a PhD and read about this, or do they go and get something like NVIDIA clothing or some off-the-shelf plugin and start there when they're thinking about how clothing and cloth moves within their application?
Well, they can get the book and write their own simulator, of course.
Yeah.
But yeah, there's a few simulators out there. There's the more researchy, math heavy, where you can actually get the code and change the algorithm, or you can. There's NVIDIA physics or other solvers that you can try and play with, or the ones in the game engines, or 3D engines such as Maya or Blender. Yeah, those are all things that you can start like open up and plug in and just start playing with the different settings.
Mm-hmm. It seems like there's a lot of source code online for this kind of stuff. Like, yes, people, I'm sure, keep them to themselves and patent them, but it's a surprising amount of people sharing their code and their algorithms freely.
Yeah, it's a pretty open community, I would say. There's definitely a lot of stuff to get started, but it's not, of course, not at the level of something that maybe a special effects studio would use, right? Because they have many years of in-house knowledge that's built
Mm.
on top of that. But if you want to get um, like an understanding of how these things work, yeah, then there are definitely codes out there that you can check out.
And that definitely juxtaposes that use case, that doing offline rendering versus doing real time game rendering on an off the shelf machine like my desktop machine, or even on a mobile device. I'm sure that's mobile cloth is an entirely different way
Hmm.
of thinking.
Yeah, it's definitely different approaches to the same problem, depending on what's most important to you or your application, for
Hmm.
sure.
Now, it's not necessarily cloth, but I did wanted to point out that you also did a paper on real time oil painting on
Hmm.
mobile hardware, how to like bring down a digital oil painting system on something as resource constrained as an iPad.
Yeah, that was an interesting project. So the idea was that we can do oil painting, but really accurate oil painting. So we have the actual fluid simulations. We have different colors that would the pigments that would mix in different way, like in like the way real color mixes, which is not the RGB way that computers typically do it. So the challenges there were to get really accurate color models and then simulate everything in real time. And then it was interesting because I worked with a lot of artists, and then I got their feedback. So they were brought into the feedback loop very early on. So they would like be like, "Oh, this doesn't look real. This does look real. This works well. This doesn't work well." So that was a really fun project.
Yeah, that sounds so interesting. These are all examples where someone can look at it naively and think, "Oh, yeah, well, how hard is that?" But when you start thinking about, runny or diluted paint and having the stroke change the paint, and that stroke, you have to have an infinite number of strokes on a really long running painting. How do
Mhm.
you optimize all those factors?
Yeah, and then you want it running on like some the cheapest hardware you can get, right? So there's a definitely a lot of challenges that you wanna solve there.
Yeah, it sounds like it's a fun space and a space that you're going to hopefully enjoy a very long career in.
Yeah, we'll see. Hopefully.
You can check out the book that Tuur Stuyck has written. I've got links in the show notes. It is a short read, about 100 pages, but it is a great overview into this space. I'll have show notes for all the things we talked about, the different papers, the research papers, as well as a place where you can buy the book. This has been another episode of Hansel Minutes, and we'll see you again next week.